It's okay now? Okay. All right. Good morning, everyone. Any questions before we start? Any questions regarding yesterday's letters? No? Everything's good? Okay, good. So for today's lecture, I will switch topic a little bit. I'll talk about the fog and the dew. So that's my personal favorite topic. When we think about the hydrological extremes, right? Very often we think about the rainfall, we think about the flooding, right? So that's of course is important. But in many parts of the global dryland, actually fog and dew play a very important role. We just don't really pay too much attention to them, right? So that's why, in the last 10 years also I've been working on this topic. I think it's very interesting. I will talk about some of the results we found and hopefully that's inspire you to think about this kind of a minor component of a hydrological cycle. So most of the work, the picture on the top is from a Namib Desert. So it's in Africa, right in southern tip of Africa. So most of the field research we done is from there. But we did do some modeling, do some remote sensing work, try to upscale the work a little bit. So first of all, why we care about the dry land, right? So here it's not technically a dry land, but the neighboring state, Rajasthan, right, is much drier, right? So when you look at the map, this global map, so all the yellow color are considered as dry land, right? So globally, dry land account for 40% of the land surface. It's very large presence. So it appears in every continent, right? So except Antarctic. So, but even Antarctic, you have dry valleys, right? So, but all the human habitat regions has a dry land, right? So when you look at India, you will actually see there is actually a big part of the country is considered as a dry land. So when we think about dry land, when we look at the rainfall record over the last several decades, for majority of the dry land globally, you can see there is actually big reduction in precipitation. Right? So because dry land already was limited, if you have less precipitation, that means it's not good for vegetation growth there. Right? So, but also make the non-rainfall water more important, like fog water, dew water. So that's why we need to care about them and study the mechanism for them. So dry land has a lot of people living on them. So globally, about 1/3 of the global population living in dry land, mostly in semi-arid and dry, humid regions. So, but it is more than 2 billion people living in dry land, right? So, but not only there are large amount of people living in dry land, actually the rate of population growth in dry land is actually proportionally larger than other parts of the world. So this figure I did almost more than 10 years ago, but essentially that is a population trajectory for dryland countries. So here dryland country, basically I just define, if one country has a dryland more than 50% of their territory, we consider as a dryland country. So the black line here, that is the global average. And you can see for most of the big part of dryland countries, their population growth rate, so that is the density, is much higher than global average. And these two countries stick out. You can imagine this is here, India, and this is Pakistan, right? So that actually give us the idea like how population trajectory in global dryland, right? So this one is not particularly promising because we know dryland is actually limited by water resources, by other resources, right? So if you have population growth that big in dryland, that's actually will create a lot of pressure, create a lot of tensions, right? So part because of that, right? We know dryland actually suffer different land issues, mostly like soil erosion, land migration, right? So it has been estimated up to 70% of the dryland are affected by desertification issues. Right? So that's tell us about I guess the status of dryland, and also the importance to think about the water resources in dryland. So, I wrote a letter to science many years ago. We talk about you are living in a not extreme end of dryland, right? So we should develop technologies more efficient harvesting rainfall. Right? So because a lot of time when people live in dryland, you actually rely on the groundwater from dryland for a lot of purpose. So we're talking about rainfall should be more efficiently used in this type of system. And also, if you move from a kind of a less dryland to extreme dryland, maybe rainfall is very small now. And so we're talking about, then you should actually start thinking about fog and dew.
There is a relationship between temperature and evaporation and the transport. So, but that's just one piece of evidence. So there's modeling, right? So we use hydrosphere to model vapor transport. It's one of the few models actually can specifically have the vapor component. Most of hydrological models we talk about is water. This one is a more component. Yesterday, some people asked me how data you can actually be trust your model, right? So this is a good example, right? We are working in a very remote area. We don't really have much data at all, right? So the only data we have is the temperature data and the soil moisture data. So we basically that's the only thing we can actually validate the data, the model at, right? So for example, on the left, that is temperature data between observation and modeling, and on the right is the soil moisture data between observation and modeling, right? So for temperature, we spot on. It's very easy to model temperature, right? So and for moisture, we are okay, at least from the from the mean value, the observation and the simulated value, they are very close, right? So that's it's not perfect. It's not like we can validate every parameter, right? But at least we validate what we have and is actually reasonable, and then we can then use that model to simulate the vapor flux, and that is actually vapor flux from a gravel plain from the sand dune, right? So you can see it's actually above zero. That means they do have a positive flux into the atmosphere, right? So that's basically give us the kind of a mechanic-based evidence to show, okay, there is a possible groundwater can transport vapor all the way to the atmosphere, right? So give us evidence to say that. So, but again, yeah, just give you an example, how much data you need to validate your model. It's really based on your question, right? So, for us, we propose a new hypothesis, and we are working on a region without much data. People are okay with that, right? So it's still publishable. So that is transport, the mechanism part. So the next part is basically reverse. So we know the groundwater can impact soil, can impact fog formation. But how about like fog impact on soil moisture? Right? So because we know soil moisture is most important parameters we think about in terms of vegetation dynamics, right? So that's vegetation need soil water to grow, right? So soil water really has impact on wildfire, on the meteorology conditions. Like for example, when we think about the thunderstorm here, that's very closely related to soil moisture level, right? So also soil moisture is responsible for like soil biochemical process, and is also responsible for like vegetation patterns in dryland. In the last slides, I will show you a vegetation pattern, how that linked to soil moisture. Right? So basically, just tell us, soil moisture is a very important component of a dryland ecosystem. So that's why we try to have a good understanding how do we and how fog actually impact soil moisture. So again, we did kind of 2 ways. So we first did observation, and then we develop a model and try to simulate that. So this is first is observation. So there are 3 locations: gravel plain, sand dune, and gravel, different type of gravel plain. So on the top, they are the fog events, and this line is the soil moisture dynamics. So what we saw here, that's the mean value variation and the fog events. But basically what we saw here, that is during the period there's no rainfall events. Like I mentioned, rainfall events is very rare in this desert. Sometimes, maybe only once per year. Sometimes there is no single rainfall events the whole year. So, but we do have a frequent fog here. And you can actually say, right, after fog events, some actually did start having small peaks. So that's already tell us, fog does play a role in terms of driving the soil moisture dynamics. So then, next step as a hydrologist, you want to be able to simulate that, and then you can do future prediction, right? So that's the goal. So, but there's nobody actually has been incorporate fog into soil moisture model, right? So you have to do that on your own. So what we did is we first try to look at the fog distribution, right? So, and then see whether we can, because if the distribution is similar to rainfall, we can then think about we incorporate the process into existing model using the principle of rainfall, right? So that's the idea. So, when we plot the fog distribution, we found is actually fit well with a Poisson distribution. So that's actually, for rainfall, actually also follow a Poisson distribution. So the unique thing for Poisson distribution is you can compose the time series into 2 components. One is basically the average rate, like how much fog you have, the frequency of the fog, and also the how much per fog event. Similar to rainfall, you can decompose to like how big per rainfall events, and also how often rainfall happens, right? So, that's a good thing. So fog actually follows the same statistical distribution as rainfall. And because of that, we were able to then modify stochastic modeling framework. So that's developed from my advisor's advisor in Princeton University. So the idea is, this is soil moisture dynamics. DS is soil moisture, and then you have the root zone, like a depth, how deep the soil is. And then you have a porosity, right? Basically the property of a soil. And then there are 3 loss functions. Right? This one is through evaporation, this is transpiration, so that's a leaching loss. In dryland, a lot of time leaching loss is considered 0, right? It's very small. And for evaporation, you basically, based on soil moisture threshold, you model evaporation. Sorry. So really, the unique thing, what we did here is we add fog into this modeling framework, right? So because fog is different from precipitation, right? For precipitation, you can use rain gauge to measure it, 1 milliliter, 2 milliliter, right? So that is a fixed unit. But for fog, when you use a fog collector, it's actually horizontally, right? So you have to do some correction. So that's why we introduced this one as a kind of a conversion factor from horizontal water to vertical water. Right? So after we modify this framework, we can then simulate fog impact on soil moisture. Right? So we can provide fog input and then see how well we can actually simulate the soil moisture. So this is results between observation and the black line is observation. So the pink line is simulated one, the model one, right? So, of course, they are not perfect, but it actually captures the major peaks, right? So that's already a big advance, right? So like I mentioned, in the past, nobody were able to model fog impact on soil moisture. right? So far we look at soil moisture, right? So, but when you think about plant water use perspective, it's not soil moisture actually play. It's actually soil water potential, because water flows through potential gradient, pressure gradient. It doesn't matter what soil moisture you have. So that's why we also look at the fog impact on soil water potential. So we use a device called WPT4. I don't know anyone heard of this, right? So it's basically a device you can put a small amount of soil sample in there. It actually will take a reading of the soil water potential of that sample, right? So give you the idea how dry or how wet the soil is. So, and then what we did is in the field campaign, what we did is we'll collect soil sample from different habitats, some in open area, some in the riparian area, some under the vegetation. So we can look at what's the soil potential before the fog events, and then the blue ones are after fog events. Right? So we can say basically regardless where we are, right? So either open space or under some vegetation, after fog events or dew events, you can say actually there is a big increase in soil water potential, right? So a very large increase. So regardless which year, right? So that's already tell us, fog actually did play a pretty important role in soil water status, right? Actually increased soil water potential dramatically. So that's the first step, right? So look at the soil water potential. And then the next step will be how really fog impact vegetation water use, right? So how do we do that, right? So we basically look at the similar idea, but we look at the soil, plant water potential. So what we did is we use a device called a pressure bomb. So it's a scary name. But the idea is pretty straightforward. You put the plants into this opening, and there is a pressure we add to squeeze the plants until water coming out. So that under that pressure, that is a plant water potential. Right? So you typically do that before sunrise. So it's called pre-dawn water potential. So that's because at that time there's no transpiration yet. So the plant water potential should equilibrium with the soil water potential. That will be the time, the maximum water potential plants have during the day. Excuse me. So basically what we did is we'll get up very early in the morning before sunrise. We'll go to the site, we'll cut the small twigs, and then we'll put them into this device, and we'll measure the pressure from the plants. And then we'll do that during normal days, right? Then we'll do that during fog days. After fog events, we'll go there again and measure it. So we did that for like almost all the major species from that region. So, and you can see basically the vast majority of the species, only I think one species, Calicarama. So only this one didn't really show like much response. But for others, it's really like a big difference between fog and ambient condition. Right? So basically, after fog events, the plant water potential dramatically increase. Right? So that's basically telling us that plants actually can directly benefit from fog events. So remember that's a twig, that's a branch. Right? So after fog events, their branch water potential increase dramatically. Right? So that means they are directly benefited from the fog water. Right? So that's a morning fog, but it's very interesting. Like if most of the fog events in this region coming from the morning hours, but there are some fog events come at night, like 9 p.m., 10 p.m. So it's very interesting for this type of night fog. In the morning when we measure water potential, plants really don't benefit from them. So it's very interesting. Like only morning fog actually benefit plant water potential. Night fog it doesn't. So we did the same thing for dew events. So basically, if you have after we have a dew events, we also go out and we measure water potential. We compare that with condition without dew. So you can say, for regular dew, there are only maybe 1 or 2 species show response. majority of them actually didn't really show response. But when we have a heavy dew events, so what we saw is actually most of the plants then start showing response, right? So to me, that's really basically telling us that dew is relatively small events, so plants won't be able to take advantage of that if the water amount is so small. But if you have a heavy dew events, that's almost like a fog now. Right? So plants can then start taking advantage of the additional water they have. So then the next thing is some plants, almost all the soil samples, right? So they show response to fog events, but not all the plants show response. So when we did a correlation between soil water potential and plant water potential, you can see most of the species, they are significant, but there are two species, they are not significant. Their correlation are not significant. So, but these two plants did actually show the response to fog water. So that's telling us, very likely these two plants at least, they actually taking up the water from their foliar uptake, from their leaves, not from the soil. Right? So for others, very likely they benefit the fog water through the soil water. Right? So, but for these two species, very likely they just directly take up the fog water or dew water into their tissues. Right? So that's just give us some indication how they use this water. Right? So, but that's a correlation, right? So it's not the most direct evidence, but point out to that direction. So far what I talked about here is mostly based on the ground observations, right? So it's based on, there are limitations. We only go there maybe a certain time per year, right? So only certain days. So how do you do that, from a more continuous level, right? So that's why also we did find the impact so big that make us try to think, move even further, whether we can use remote sensing to actually do that, right? So that's our next step. We want to say, if the impact of fog on vegetation is so big, whether we can see that from space. So that's what we try next. We're basically using remote sensing to look at whether fog has an impact on plant greenness. So we choose two sites for the remote sensing application because that's the part you have the dry rivers. So there are more vegetation because a lot of the sites, if the vegetation is so sparse, remote sensing won't be able to tell from vegetation and the background. Right? So the index will be very noisy. So we choose these two sites. One is the global map side, one is called marble copy is here. So what we did here is that is a time series of, at the bottom is all the fog events. And then on the top, that is the EVI value. EVI basically is the enhanced vegetation index, right? So in a nutshell, that's basically give you the greenness of that region, tell you how much plants are there, right? So that's EVI. So we use EVI, we use VOD, right? So that's an optical vegetation optical depth. So this one is just a different wavelengths. Right? So this is more like a microwave wavelengths, and this is more from the regular wavelengths. You can see it. So, but anyway, so we use a different indication of vegetation growth. So what we saw here, you can see there are already some indication when you have fog events, the vegetation index starting bigger, right? So that's already gave us some indication. And then building on this, we can run some statistics, right? So for example, we can on the x-axis is the fog amount, so that is a ground-based measurement fog amount. And y-axis is the NDVI or EVI or VOD. They are all indicator of vegetation growth. So you can see actually there is pretty nice. Pretty nice means is a statistical significant relationship here, right? So they're noisy because the is a dryland vegetation. The number is very small, but we do say in both sides there is a strong relationship for the between fog number and the vegetation number, right? So what that tells us, right? So that's basically means the fog impact on vegetation is so big you can even detect that from space, from satellite information, right? So that's never has been done in the past, right? So that's quite exciting, right? So for this one, we didn't see the relationship because we think is because this side actually has a much lower vegetation cover compared to this side. So under this type of a low vegetation cover VOD data, the quality is not good enough to be able to representative enough. So I mean that's always a challenging aspect working in dryland. You work with very small numbers, right? So you have to be very sensitive to be able to see that. And this is from the real image. So basically before, this is the before fog events, this after fog events. Somehow the label is gone. But just give you an idea, even using naked eye, if you look closely, you actually can saw the difference. Of course, it's not big, it's a small difference, but you actually can see that from the satellite image, right? So that's to me, it's a very interesting, right? So because you can actually tell the fog impact from satellite observations. So, but so far, when we look at the impact of fog on vegetation, the vegetation part we got is from satellite information. But for the fog number we got is through from ground observation. So ideally, if you want to do that relationship much more broader scale and more continuously, you should be able to get fog number from satellite as well, right? So that's not easy as well, because there are some sensors they can actually based on the similar as NDVI, you can actually use the sunlight like reflectance to look at the fog. But the problem for that is you don't know whether if you have a satellite on the top, if you have a cloud there, you get the reflection, but you don't know whether these fog events actually touch the ground, this cloud touch the ground or not, right? So because the fog is by definition is a ground touching clouds, right? So that means the cloud has to touching ground. Using regular remote sensing, you can't do that. It's very hard to do. So that's why the next step we did is actually try to think about whether there are some other ways, some newer technologies we can rely on to be able to basically using the satellite to looking at the fog, looking at whether fog touching the ground. So what we did here is there is a less used, but is a NASA satellite called Calypso, right? So the unique thing for this satellite is active. They actually send the lasers, right? So it's not like a pure reflection of sunlight. It's actually active sensor. So they send actually laser all the way through the clouds. So because of that, you have a very high resolution of the scatter. So that means if you have so they give you the ground surface, and then you can actually look at this is the fog events. The white color is the fog events because of high water content, and then you can actually say, okay, here this one. If you look at this location, that's a fog, and this location, that means there's no fog. There's no fog, right? So this is the ground surface, and also one of the challenge for like using remote sensing to doing fog is like mentioned low clouds, right? So because if you have low clouds, they don't touch the ground. From regular remote sensing, you can't differentiate whether that's low cloud or fog. But for this type of instrument, this type of measurement, you actually can say, okay, this actually is a fog event, and here is a low cloud. You can actually differentiate that. The reason you can do that because this is a laser, right? It's not affected by the cloud blockage, and you have very high resolution vertically, and look at the scatter of the signal, right? So This one, yeah, all the data we work is actually all public available, right? NDVI, VOD, EVI, even Calypso data, right? So the only difficult part is this is a very large amount of data. You download, you process yourself. That's actually a very large data amount of data you have to process and be able to look at it. So, but if you can do it, it's very powerful. You can actually looking at the differentiation between fog events and the low cloud events. So after we actually looking at try to detect the fog, we can see how well we did. Right? So in this one, the x-axis is basically the signal from the satellite, the backscatter signal. The y-axis is the ground observation of a fog. So we can say we can more or less capture the events reasonably well, right? So it's not perfect. Again, it's R² 85, right? But it's already big advance. You can actually using satellite data directly derive fog water, right? So that's that is useful advance in this aspect. But limitation for this is for Calypso data, right? So their laser data is quite valuable, but they're like I mentioned, satellite data always has trade-offs. So they have a very low frequency. For our side, we use 10 years data. We only found several data overlap with our station. Right? So that's still in theory we can do it, but in reality, because of the limitation of the amount of data, we still can't do like global application yet. So the last bit I'm going to talk about is, right now we already know fog impact vegetation. We can even see this impact from space. And also we develop ways try to detect fog from space. But then really another big question, we still try to answer is, because we know rainfall is still there, right? Even is a small amount, rainfall is still there. How relative like a fog and the rainfall play a role into the vegetation dynamics, right? So that's that's a part is still very important. How do you quantify that, right? So that's the last bit I'm going to touch on. So we basically try to find ways to quantify the relative importance between fog and the rainfall for the vegetation changes. So what we did here is basically based on remote sensing data. So fog is a ground-based data, but for vegetation and rainfall is a satellite-based. So here we use NDVI, like a Moody's NDVI, right? So that is a 500-meter resolution. You have an 8-day resolution. Every 8 days, you have one data point. So for rainfall, we do have a local ground-based rainfall measurement, fog measurement, and soil moisture, soil temperature, wind speed, and we calculate the VPD. Right? So, and then what we did here is besides just using NDVI, we also use the first derivative NDVI. So basically that means you take difference of this day's NDVI from yesterday's NDVI, right? So by doing that, really give us the growth rate, right? How vegetation growth has been changing. It's more rather than the state variable. You have a rate variable. Right? So what we did is, we try to rank the importance of all these variables using random forest. But building on random forest, we can also look at their interaction between these variables. How do they interact with each other and impact vegetation? And here are the results. So this one, the left is the results from NDVI. On the right is the first derivative NDVI. So this figure is made through R package called Vivid. So I highly recommend it. It's quite powerful in terms of the information you can get. So you run random forest first. After that, you can actually look at the interaction between all these variables. That's all the lines represented. So the thicker the line means the stronger the interaction you have between the variables. And then you have the size of the circle, right? So the bigger the circle, the more impact of this variable has on vegetation, right? So that's the meaning of this graph, right? So when we look at NDVI information, when we look at NDVI, we can see actually for cumulative rainfall, right? So the circle size is much bigger than fog, right? So basically we conclude, for NDVI value, actually rainfall is still very important, play a more important role than fog. But when you look at the first derivative, right, we use this one as a growth rate of plants. You can see if you use the growth rate, fog actually play a much bigger role compared to rainfall. Right? So that's actually quite interesting, right? So basically it means for vegetation changes, fog actually play a very important role here. So again, fog actually, the power for this analysis is not only tell you how important of a single variable on vegetation, it tell you how this variable impact others. Right? So you can see fog play a very important role in terms of interacting with others. If you have a fog events, means very likely you change soil temperature, change wind, change VPD. Right? So that's actually give you more comprehensive information, the interaction between all the variables, how do they play together, impact the vegetation. Right? So that's is building on random forest, but more powerful than random forest, give you more information. And then building on this, we can use so-called partial dependence plot, right? So essentially, you control all the other variables. You only allow the variable interest to you to change, and see how this variable changing the parameter you are looking. And for this particular case, we have a rainfall variable, temperature variable, wind speed variable, VPD, and the fog. So we're looking at how these variables changing NDVI. Right? So basically what we saw here is if you think about total NDVI, right? So the rainfall play a very important role. As rainfall increase, NDVI increase, right? So that makes sense, right? More water, more plant growth. But when we look at the first derivative, that's the bottom. So that's a change of vegetation, basically the vegetation growth rate. When we look at that, you can see actually the cumulative rainfall still is a positive relationship here, but not very big. Actually, what really matters is actually fog events. And so it actually has a pretty strong impact on the vegetation growth. Right? So that's just to tell you, you can isolate, different variables and only look at the variables interest to you. That's what the partial dependence plot can tell us. So basically, these two together tell us rainfall is still important for sure, but actually fog play a very important role in terms of maintaining the vegetation growth. So that's basically this type of study telling us, this type of analysis telling us. Any questions so far? Okay, so I only have a couple more slides left. So far, what we talk about is fog impact, right? So we talk about ground observation and the remote sensing application. So we didn't talk about the deal too much, but I just want to point out, deal actually, we have a project right now actively doing 4-year project looking at the deal impact on vegetation from flux tower measurement and hopefully from remote sensing measurement as well. But this slides basically try to tell you is we know temperature is increasing, right? So globally, so that means you increase the dew point temperature. Dew probably will be harder to form. So that means in the future there may be less dew in formation. So and this one I just want to show here is this is a global warming experiment. Right? So we know when we try to understand how global warming change the ecosystem, carbon sequestration, or other things, we use a controlled warming experiment to do that. Right? So, but here is a study I was involved. We were talking about like if you have a control treatment and a warming treatment, right? You actually the warming treatment significantly reduce the dew formation, regardless what kind of substrate you use, either artificial like plastic or vegetation, or this is a wetness, leaf wetness sensor. Right? Depends regardless what type of technique you are using. So that's all like telling us in the future, very likely dew formation will be declining. But that's also tell us, in the past when people doing the global warming experiment, right? So they never really like consider dew formation as a part of the process. But in fact, because dew is reduced in that case, that means they may overestimate the impact of global warming on some of the parameters because they didn't consider dew formation, and the dew formation does change carbon flux and nutrient dynamics. Right? So this just gives you an idea how the warming works. So, but that's just the idea about the dew, right? So, just touch on this and talking about what will likely happen in the future climate condition. Under warming, likely will have a less dew formation, right? Really, the last slide is I have to mention is if you, I don't know how many of you guys heard of this fairy circles. Anyone heard of this? Nobody heard of this? Okay. So, yeah, this is one type of vegetation pattern, right? So that's actually, this one is from Namib Desert, from the one I'm working. You can see they called fairy circle because nobody knows exactly how this thing form. That's why they think a fairy makes them, right? So that's basically grass circles. So they are maybe 1 meter, 2 meter in diameter. They are different size. And there are millions of them in the Namib Desert. Right? So people still try to understand how exactly these circles form and evolve and break down. Right? So some people hypothesize that termite is actually the player to form this. Termite eats the grasses in the middle and then form this type of circle. But others think it's not termite, it's actually vegetation itself, is a vegetation self-organization to be able to utilize water and nutrients more effectively. Right? So that's two groups, they try kind of debate with each other. But this one just give you a good example under very extreme environment. Right? There are many vegetation patterns happen. You can use mathematical models to model this. But as an eco-hydrologist, what I try to understand is how this type of vegetation pattern get affected for eco-hydrological process. Right? So that's what we did, the observation. Collaborator is Sujit Ravi. He's from India originally. We went to graduate school together, and he's a professor in another university. We traveled to my site together. We made quite a bit of measurement. So, the big measurement, the major measurement we did is one is the soil moisture. Right? We looking at the soil moisture inside and outside. And also we measure the infiltration rate, how fast soil can go through. We measure the infiltration in the middle and outside. And also what other things we measure is soil texture, so the particle size distribution. Right? So basically how fine or how coarse the soil is inside this, in the circle and outside. Right? So what we found is that are very interesting is soil moisture is much higher inside compared to outside. And the soil is much coarse like inside the circle compared to outside the circle. And also the infiltration rate is one magnitude higher inside the circle than outside the circle. Right? So based on this, our understanding is, our results we think more supporting the idea of vegetation self-organization. So because the way they do, we think is, when you have a big wind, the wind actually will blow away the fine particles outside, and they will deposit outside and also on the grasses. And then in the middle will be coarse. The soil will be very coarse. So because of that, when you have a rainfall events happen, and water will easily infiltrate inside this soil column, can store there. Water can store there as a reservoir. So then plants were able to utilize that water when environment is very dry. So utilize as a kind of a water pool there. So when we dig up the plant's roots, you can actually say, the roots inside is much longer, outside is very short. So it's actually very long roots and very short roots outside. So it's all kind of supporting the direction. That means vegetation does organize this way to be able to utilize limited water resources, like in this type of environment. Right? So, including fog, because that's a happen in fog zone. So, yeah, to me, just very interesting to think about the nature wonders. How do they form? Right? So we didn't solve everything because we know when it happens, that's what happened to hydrology, to soil condition. But we don't know how initially they start. Right? So that part we still don't know. Right? So it's still worth like further investigation. So just a quick summary for everything I talked about today. So basically using isotope as a tracer, what we show here is fog and dew actually has multiple origins, right? So some come from the ocean, some actually come from the desert itself, from groundwater. And so there are some is a mix water origin. And also we talk about, we can both soil moisture and groundwater, they actually potential source of water for fog and dew formation, right? So we use a modeling approach to show, you can actually transport the water through groundwater, through relay process to be able to release the water into atmosphere. Right? And also, based on field observation, we can say the fog actually has a pretty big impact on both soil moisture and water potential. And we did develop a modeling framework. We can actually even model the fog control on soil moisture dynamics. Right? So the good thing for that is we can predict in the future. Right? For example, based on temperature, based on other parameters, if we know how that will impact the fog, we can use our modeling framework then predict how much soil moisture will be affected as well. Right? So we talk about based on field observation, we actually show both fog and dew, they can actually increase plant water potential and basically provide some direct evidence that plant can directly benefit from fog water and dew water. But we did saw the timing of the fog does matter. And I show you for the night fog actually doesn't really impact vegetation water potential next day. But for morning fog, they have a very big impact. And then we talk about it, right? So fog impact is so big, we can even actually using satellite information from space to be able to look at the impact. Right? So then lastly, we use basically statistical framework, try to kind of quantify the relative importance of fog water and rainwater on vegetation dynamics. So what we saw is if you think about the status variable, like NDVI, so rainfall is actually very, very important, more important than fog. But when you look at the vegetation growth rate, when you use the derivative of NDVI, actually fog play a more important role, much bigger than rainfall. Right? So just give us some idea how rainfall and the fog kind of complementary to each other to be able to maintain the ecosystem dynamics. Right? So that's based on statistic analysis. So yeah, I guess lastly, I just want to again acknowledge our funding source through National Science Foundation. So this is a 5-year grant. So but we did a field observation for more than almost 10 years, and the IAEA for the isotope work, and from the field station, they actually provide a lot of logistics for us for field work. And some group members, they are involved, when we measure soil moisture in the field, we have to set up the soil moisture sensor ourselves, things like this. And there's the student has been working in this project for modeling, observation, and other things. So I guess that's all for the morning first lecture. Any questions? Okay. So yeah, hopefully you'll find this interesting as I do, right? I always think they are understudied. So for gonna deal, they are the least studied hydrological component, right? Nobody care about them, right? So I think it's very important for us to be able to have a better understanding. How do they form? Where is water coming from? How they are changing? That's we require measurement, require modeling, require like other observation. So hopefully some of you guys will be interested and continue this type of research. So again, I'll be around for a little while, and if you have a question about the specific aspect of this, feel free to come to me. We can talk about it. All right, thank you guys. Thank you.
Sir, how can measure the quantity of non-rainfall water?
How do we quantify? Measure it. So for fog, we use fog collector. Have a picture in the beginning. So this type fog collector.
The government and data collecting agency will collect the non-rainfall water.
Yeah. So this one has a very high surface area.
If I want to get the non-rainfall water,
Yeah, you can set up we have plenty of them.
the government have data or not? The government have data or not? Non-data.
No, I don't think anybody collects them. That's why
No one
collects them. You have to collect yourself. Yeah. That's why it's hard to do. But I think we should do it. Yeah. So it's actually when you look at the hydrological budget, depends on where you are. There could be a significant budget. If you miss them, you miss quite a bit of water. So yeah, but
So non-rainfall water is fog, snow, dews.
I mean, snow considered rainfall water.
Snow considered
Yeah,
fog,
yeah.
dews,
Fog, dew,
dews, and
and water vapor absorption.
water vapor, and
That's it. That's only three.
that's the
Yeah.
non-rainfall water.
Yeah. So, but the water vapor absorption is so small. Really, the major player is fog and dew.
If I get data, then I will collect primary data by itself.
Yeah.
If I go through the non-rainfall water.
Yeah.
Thank you.
No, you can identify the error curve. Right? One is we didn't use classified. It's unsupervised.
Okay, unsupervised.
Yes.
So you got the data from any source? So
We collect them ourselves. All the meteorology variables. No. The weather station is actually public available. You can actually download the data yourself too. Yeah.
because I was working on my area, so I was not getting. So I have to use the supervised classification.
Okay.
That data was not available. So that's why, because my work is also on LUSC future
question.
Sir, my question was that for that random forest, you use supervised classification or you not used?
Okay.
And if you use, then how many samples you have taken?
Okay. Okay.
You were telling that you have used unsupervised
And
classification.
supervised. Yeah. Yeah.
Sir, yesterday I asked you about soil organic content. So you told me we can do like no tillage drip irrigation system.
Sure. Yeah. Yeah.
But the problem is like how to do awareness of that among farmer, because the farmer use the same old traditional techniques, and also the drip irrigation system you set up is expensive.
Yeah, I mean for initial investment is quite big because for no-till, right, you have to find a machine to be able to do the seed. Is different from the traditional. But then maybe but if a farmer don't have a big field, like in the US, if a small field, then it's still doing it himself. So it's not big investment in that sense. So it depends on how big their field are. So yeah, it's really, if they do by labor themselves, it's almost zero cost. They just harvest all the crop and don't do anything. And then next year you plant yourself. It's actually okay. So maybe you can convince them that way. That means they save by seed. They don't have to plow themselves.
And also they use like so much of fertilizers, chemicals. So like how like we promote them in a large scale to use organic farming.
Yeah, I heard I know maybe in India the same thing. I heard Pakistan the government gave a lot of subsidy for fertilizer.
In India also they give.
Yeah, okay, that's the problem. Then people don't care. They just put along. Yeah, I guess I don't. Yeah, I guess I don't know what's the best way. I mean, in US really just government don't have any subsidy for fertilizer. It's very expensive. So farmers, they don't want to waste their money. Right? So yeah, I guess maybe just from policy point of view, you have to talk with the government. Basically say you can still do subsidy, maybe not as much. Then farmers can, also you can do some experiment to show the farmer. Like if you reduce the rate, it doesn't change the yield. If you show them the data, they say, okay, maybe we'll save the fertilizer for next year.
Yes. Like we have to show them visually expert talk and collaboration with agriculture universities institute. Our awareness is not there, sir, in India especially. This is one of the major problem. Because government of India, like they are promoting organic farming and startups, and they are also providing many schemes and fundings.
So I know but agriculture is a huge potential, right?
Yes,
so
sir.
for environmental issues or climate mitigation,
Yes, sir.
there are many things you can do. So that's good to think about that direction.
I want to contribute to society in this agriculture sector, but like I'm not getting the idea that how to start all this problem, solution of all this problem.
Yeah, I mean, you can't solve everything. You have to just do one aspect and do it. Right? So like no-till, you can read some papers, maybe write a summary, and give to farmer and show them, that's actually, the yield doesn't change. At the same time, you save a lot of money, you save labor, things like that. And maybe for fertilizer, you can either do some experiment yourself, like a plot experiment, or you just find data from literature to say, if you reduce fertilizer by half, the yield doesn't change. So there are data there. So in the US, there are people doing that. You can search literature and say, for your soil, you don't need that much fertilizer. You can show them.
But one more problem is there, sir. Farmers are like, most of them are illiterate. So like, I cannot explain it in very technical terms.
Yeah.
I cannot explain them in their local language, like layman, like this is the solution. This much yield you can get if you adopt these techniques.
I mean, you don't need like a scientific language.
Yes.
Right? You can just say, if you don't do the plot, and you actually don't need to do that, like you save your labor in the fall.
Yes.
And, it's actually good for the soil. You don't lose like a soil anymore. You tell them, soil is actually non-renewable resource, and if you lose them, you lose them forever. Right? So people don't think about that way, but it's actually, worldwide we have lose so much soil. They form millions of years. If you think about the human lifespan, if you lose them, you lose them. Right? So you can see, for your future generation, so they run out of soil to grow crops. You have to think about that.
Yes.
So I'm glad you're thinking about that.
I'll need your guidance also if like I do some work.
Yeah. Happy to try. Yes. Sure.
Sir, I want to know how fog and dew is affecting irrigation requirement and at what scale?
That's a good question. I think depends on where you are, right? So if they are not huge, the amount, right? So I think in most of places it probably doesn't affect irrigation because for agriculture you just use a lot of water. The amount of fog and dew probably is a very small proportion. I'm more talking about the natural vegetation. They don't really have a outside water sources, right? So they have to rely on rainfall or fog or dew. For them, it's kind of very important. But for agriculture, people always get water. If there's no rainfall, they use groundwater, right? So then fog and dew will be very insignificant.
Actually, sir, in calculation of crop water requirement, generally some things like water runoff and this dew and this fog, we don't assume this in the model when calculating crop CWR. Generally, we mentioned that its number is too small, so we neglect it. But during a time, like in the month, in the December, January, February, during that time, sometimes long hours of fog and dew. At that time, we
And
have
also in summer, I think dew almost every day. I don't know here, but in many parts of the world, it's like that.
in general, just like 4 or 5 months, you find a dew.
So I agree. That is actually significantly enough amount of water there, but just nobody calculates that.
Can it be a base for sampling for finding CWR annually or monthly or seasonally? For example, during in the month of October to January or February. At that time, for these 4 months, we can assume the contribution of fog and dew, and we can create, calculate the CWR
That would be good.
and compare with the previous,
Exactly.
the second.
So you can set up this kind of thing for collect fog, and then you can just do like a very cheap